Welcome to this presentation on future video coding, the MPAI end-to-end video coding project. So this is true for my future, but then Min will run the seminar with the same title. Who is MPAI? We are a not-for-profit organization incorporated under the laws of Switzerland with a mission to promote the efficient use of data by developing standards for coding technologies, for any type of data, especially using technologies such as artificial intelligence, technologies, the integration of data, the information and communication technology system. So this is the technical part. Less technical part is the effort to bridge the gap between technical specification and their practical use. We do that through intellectual property guidelines, such as framework licenses and other instruments. So how do we develop a standard? So we start with an idea. This happened for end-to-end video coding. By the way, it's now quite a few years ago. Then we develop use cases. We develop the functional requirements. And when functional requirements are ready, we develop what we call commercial requirement, which is our framework license. We call for technologies, and then we develop the standard. When the standard is mature for almost ready for publication, we publish to get the comments from community, and finally we publish the specification. Where we are now with this project? Well, we are what is called here stage 0, stage 1, stage 2. Mostly, I would say, the functional requirement, which consists in testing. Developing the functional requirement, but also testing how they can be implemented in a particular way. So this is not something that I'm going to present, but it's just to explain to you what the scope of standard that MPAI is developing. We have standard for health, dashboard, for audio, for connected autonomous vehicle, for end-to-end video coding, but also for AI-based enhanced video coding, and so on and so on. You see the color indicated the different state of development. So the standard for today's seminar, what is this? In 2022, we made the decision to develop a project for an end-to-end video codec that implies entirely based on end-to-end optimized AI models. We had increasing attention from both academic and industrial entities. The project is open to non-members because it's still in an exploratory phase. It had several phases, technical phases, called the EEV 0.x, each improved in performance, and the latest one, 0.6, outperforms the VVC in random access model. You don't find it here, but many papers were published in international conferences during the years to inform the world of the progress in this project. Currently, we are working to extend the framework to a next phase, EEV 0.7, and we are looking for another jump in rate distortion and model robustness. This seminar will review what has been learned avenues. This is the last participation in the EEV meetings. So until the time a call for technology and the framework license are not published, participation in EEV meeting is open to interested parties. After the responses to the call are received, participation in EEV meeting will be limited to MPAI members. But you know, MPAI membership is very accessible. 2,400 euros for principal members and 480 euros for associate members. A last point, the presentation are recorded, but the discussion after the presentation will not be recorded. With that, I think I can start my presentation and leave the floor to Trenmin.
Okay, so now it's my turn to share. Hello, you hear me?
Yes?
Okay, so now so I am sharing my slide. May you may see the slides.
Yes, I do.
Oh, cool. So now, thank you for uh, offering this opportunity to showcase what has been happened during the past several years in the MPAI end-to-end EEV um, project. So, in today's talk, I will show you that some basic disciplines and achievements that has been made by this group. So, given this outline, in the first, I will give you the background and the big picture of MPAI EV. So, what is the why we conduct the end-to-end neural video coding and why we established the MPAI EV. So some of it has been introduced by Leonardo. So the second part is that the EEV verification model evolution progress since the very first model to the fourth model and building this foundation between 2021 and 2024. And in the third part, I will specialize these applications to drone video coding, and we have established a benchmark for unmanned aerial video coding benchmark in the Data Compression Conference 2024. And so for the final part regarding the EV 0.5 and 0.6, we transfer our research focus from unidirectional video coding to the bidirectional neural video coding, and we have achieved several papers that has been published in the ACM Multimedia 2024, the International Joint Conference on AI 2025, and the Computer Vision and Pattern Recognition Conference this year. So finally, I will give you the conclusions and the future directions of the EEV project. So at the beginning, I will show you that the MPAI EV is the first video coding standard for the fully neural network solutions, and primarily we started this project since the late of 2021 and early 2022, and we have our goal in mind is that we should build this leading end-to-end video coding standard. And in 2022, we have finished the first three major reference model EV 0.1 and 0.2 and 0.3. And later that year, we transfer our study to the drone video coding method, and we have established a drone video coding benchmark in the DCC. I think this is a typo. It should be the 2020 DCC 23. And regarding the fourth version, we have published our paper in the TCSBT 2024 and followed by some other advanced models. So since the year of 2024, we switch our study focus from the low delay P based configuration to the random access configuration, which is a P-frame based coding to the B-frame based coding. And for the both of these two different settings, we have realized is a better coding performance than the H.266 model, and which is the VTM reference software. And so the first part is the background and motivation. So this picture is a very famous one, and in the traditional video coding, we have H.266, and we have AVS, and we have AOM or AV1 or AV2 related standard. So here is the bottleneck, which is the handcrafted traditional coding, and we meet some bottleneck. And so we find out that end-to-end optimized neural video codecs would be a very promising future direction. So The goal is to build an end-to-end optimized coding standard framework and with the key characteristics of a fully neural network solution and end-to-end optimization for the bit rate and the quality. And we have the content adaptive learning and to adapt to some specific scenarios such as the drone videos or the UAV videos. And we have an easy way to upgrade because we are continuing a software-based framework, so it's easy to update our model every now and then. So it is established in earlier 2022, and so far we have gone through 4 years since our first version. And so in the early stage, we're focusing on the P-frame based coding from the 0.1 to 0.4 model. And this model is known as the OpenDVC, which is an open source version published in the early years. And this is a publicly available implementation. And we have several key components. And as a starting point for this EEV model. And so it has some key components, the motion estimation, the motion compensation, the residue encoding, and the training with a relatively large scale data set. So basically, this model has comparatively performance with the AVC or H.264. And since earlier 2022, and we have introduced the enhanced motion compensation prediction using the prediction refinement with the coarse-to-fine residue modeling and in-loop restoration network built into the EV 0.2 and 0.3 framework, respectively. So as you can see, from the very beginning to the third version, we actually have some incremental modules assigned to this framework with some advanced performances. So when we encountering the first version of EEV, so we introduced the advanced motion representation via the motion decoupling, and we introduced a two-stage motion representation. And one is the motion prediction from the temporal context information, while some convolutional STM module as the CoAuth version. And sorry, let me turn off the automatic switch from the slide. I think wait for a moment. Let me restart my sharing. Okay, here we go. Okay, here now. So when we move into the fourth version of the EEV reference model, and we introduce the two-stage motion representation. One is the motion vector prediction, which is from the temporal context via some convolutional STM module. This is used for CoAuth motion. And the second part is the motion difference. So we use the fine motion correction module to correct the prediction error of the motion information. And we have some additional modules such as the feature embedding and the feature restoration for compact latent representation, which means that our operation point or operation models are the latents of the image rather than the pixels of the image. And we have also some spatial temporal interprediction enhancement module. So therefore, this is a milestone. This is a milestone for EEV, and it has surpassed the VVC reference software VTM using the P-frame or the low delay P configuration. So this is the overall framework, and using the PSNR RGB reference as the quality metric, as you can see from the JCTVC Class A to Class E, we have averaged performances with respect to the EV 0.1 model. And after that, we have specialized applications to the UAV, and we have made the first comprehensive benchmark for learned UAV video coding, which is accomplished as a milestone for this project. And this dataset and benchmark has 14 video clips from 4 different sources, which is the very strong video from the single object tracking and multi-object tracking, and the corridor dataset and the UAV the DT dataset. And for them, we have established several contents with different characteristics from low resolution to very high resolution. And it has, for example, different light conditions, different viewpoint, different distortions of the lens, and different capturing conditions, and different content. For example, for some rural area, for some urban area, for indoor scene and for outdoor scene, and the low height and the higher capturing condition. And this is a very comprehensive data set. And this is the specific challenges for those videos. For example, it has large motions from the drones, and it has fisheye lens distortions for some indoor scenes, and it has complex backgrounds and different daylight conditions for different contents. So this data set is very challenging, and the benchmark reveals how a codec performance would be when evaluating using those video clips. And after that, we have transferred our model to EV 0.5 and EV 0.6 with bidirectional motion prediction. And the first model is the EV 0.5. Our research focus is shifted from the P frame to the B frame. And we have proposed a scaled hierarchical bidirectional coding structure using the parameter shared motion codecs and the shared motion prior, and something like trustworthy motion modeling. So here is the thing, and for this image that is being compressed, and we have introduced its front and backward reference picture, and we generate the forward motion vector and the backward motion vector respectively, and both of the forward motion, backward motion shared the same parameters for encoding those motions. And we conducted the motion compensation respectively. And here is the innovation part, and we introduced this trustworthy motion modeling as the decoded part, partial decoded result from the motion decoder, and which is an element-wise parameter ranging from 0 to 1, and with closed interval, which indicates that how confident you are when you're fusing your motion predicted pixels when you are fusing the forward motion and backward motion. So after those motion compensation, you can generate different scales of motion priors. So here is the forward motion from 1, 2, and 3, and the backward motion has a similar operation with respect to this part. And for the residual encoding, we have using those motion priors as conditional information to encode those videos. So that would be the overall flow chart of this EV 0.5 model. And furtherly, we have revisited the model has been investigated in EV 0.1 to 0.5, and we have pointed out that the EV needs to explore high resolution and random access configuration coding solution. So this is the overall framework that has been our overview paper, and so we have introduced the real unidirectional and bidirectional prediction model, and we have introduced optimization for those technologies for neural video coding, such as online learning, content adaptation, and variable rate bitrate encoding with control and perceptual quality optimization and model quantization. And furtherly, it needs some system design, such as edge computing, mobile computing, and semantic communication that supports different use cases. And furtherly, it has some standardization in some related studies, such as the EEV and JVET and ABS and the JPEG AI and something like that. And we have introduced some comprehensive evaluation in those model. And for our latest research, and we take a systematic approach from the perspective of reference information modeling, and we optimizing the representation, the translation, and the harmonization of the reference information. So here is the details. First of all, we have introduced a spatial temporal anchor-based motion estimation that is used to represent the quality of this motion vector or reference information. And then we need to encoding them using multi-scale reconstruction, flows and confidence score, and which has been introduced in the previous version of our EEV. And this is a very innovation part because that we have found some large motion, especially in high resolution videos, we need to carefully handle those motion part because it is not easy to encode those contents with large motions. So in our solution, we introduce the multi-scale with 3 different spatial resolution of motion vector to represent those complex motion information. And at the decoder side, once you have encoded those motion part with different resolution, you need to harmoniously fuse or aggregate those reference information. So we introduced the bicontextual asymmetric harmonization, and for the forward warping of those motion vector, you need to generate a coarse version of prediction with some sort of confidence map to indicate pixel-wisely indicate whether how would be the prediction accuracy for each position. And the same things goes to the backward warping. So here is the confidence map. As you can see, for some boundary part, the confidence is less confidence dense enough, but for the background part, and it is has very high quality prediction results. So the following thing is that you need to fuse them for both the forward prediction and backward prediction and to generate your contextual content enhancement. So here is the entire total framework for this reference information modeling from the representation using multi-scale representation and how you translate those motion information and how to make a harmonization between different directions of information. So this is a hierarchical B-frame-based coding framework, especially designed for high-resolution videos. So here is the overall framework, and we compare this model with the DCVC, which is published by Microsoft Asia, and we have also compared with the VTM and the HM, and with the EVV Inc. Different software. As you can see, for 4K videos, the JCTVC class A and the JVET class A2, and we have achieved a very high performance, especially respect to the random access configuration using a group of pictures of 32, and the quality metric is using the PSNR RGB. So this is a very advanced module published this year, and our paper has been selected as a highlighted paper in this year's CVPR conference. We also introduced this work during this conference and attracted a lot of attention from both industrial companies and academic societies, and we would quickly make it public available for this implementation for the reproducible research, and this is a very encouraging result. And regarding the future direction of EEV 0.7, we have listed several points that would be considered in the future development. First of all, this would be a semantic confidence modeling, and we would extend the confidence estimation from pixel level motion to the object level scene understanding for better spatial temporal consistency. Because pixel level information only indicates the error between adjacent or between the reference pictures to the current pictures. But but object level motion and scene understanding will introduce the semantics of the videos itself. And we would also consider some sort of advanced ray distortion model to broaden the adaptive fusion to the GOP level, GOP group of picture level to achieve optimized bit location when we're encoding the entire framework. And we also want to learn some lessons from some related work to realize the real-time edge deployment and to prove this EUV 0.6 model on demand to satisfy the computational constraints of some edge computing devices, especially some mobile computing devices. And for the fourth part, and this is something like video coding for machine, but we would like also to consider how to make it harmonious to different machine vision and perception algorithms and treat it as task-aware coding and compression and incorporate some sort of downstream vision semantics into the confidence modeling when you are fusing the backward and forward reference information and bit location to enable joint compression and analysis compression. So there is a lot of study that needs to be done in the future for EV 0.7 or even the later model. So to conclude this talk today, and for EEV, and we start from an open source model, OpenDVC, to high resolution neural video coding, EEV 0.6. Some key achievements that has been made is organized as first, we have surpassed VTM, VVC, H.266 standard in both low delay P and random access configuration. And we have also established a drone video dataset, which is the first learned unmanned aerial vehicle coding benchmark that would facilitate related research. And also we have again and again to realize top publications such as the journals and conferences in related venues. So we are continuing to achieve and better results and future studies to continue this project. And I think that's all about the presentation today. And thank you for the time to listening this talk.
Thank you, Chunin.
Thank you.
Very good. It was a 30-minute overview of many hours and years of activity. So I must say that when we started, we were very far from the performance of anything comparable. But now we are proud to say that we have above, and you know, and the path is only the beginning. It means that we have more that we can hope to achieve.